Hey everybody. Alright, so we're continuing chapter 4, which is cyclic alkanes. And we want to talk about more on cyclohexane. Most of what we're talking about from here on is cyclohexane, and a little bit of the higher alkanes like cycloheptane and cyclooctane. Alright, so we talked about how to draw cyclohexane. Let's practice one more time. Usually, what I'm trying to emphasize is when we draw these two lines, that we should they should be relatively at the same level, I guess. And if I'm using my top line here as a reference, it's roughly going to be like that and like that, and they're angled, right? So what I'm trying to say is, like, one is not like substantially lower or higher than the other. It's roughly about the same, all right? And then let's practice this again. Usually the way I draw it, and the book has some other tricks on this. What are the book tricks? They're in the book. There's a part in the book where they talk about how to draw this, and I just have my own method that I like. Start with the two lines, and then we kind of connect the bottom left to the top right, sort of in the direction like that. Okay, and then we connect these guys like that. Now notice a couple things. That's parallel to that. This is parallel to that, like the same angle. This is parallel to that. You always want that to happen. With practice, you can just do this. You know, like I can just do this, and you know, eventually you can do it with one hand motion, but that'll take a while. If you're bored, you know, watching TV and get a piece of paper out, you can practice this 100 times and then you can just do it, right? Okay, so then we have 6 axial and 6 equatorial hydrogens. They're going straight up and straight down. Straight up, straight down, straight up, straight down, straight up, straight down. And then we have the equatorial, which are parallel to one bond over. So, like, if I look at, maybe stop at the top right, it's going to be parallel to one bond over, which is like this CC bond. And so, and by parallel, I mean it's the same angle. The same angle. So this angle is the same as that angle, right? And it's also the same angle as this, okay? And then this one's parallel to one bond over. Where's it going to be? It's going to be parallel to this bond, so kind of like that. Okay, usually the middle ones I do last, because they're the ones you screw up. And then like this one, bottom left, parallel to one bond over, is going to be parallel to this and this. And then from the top left, parallel to one bond over would be parallel to this and this. Alright, so oh yeah, the middle ones. So those are parallel to one bond over also, and they're like extending away from the cyclohexane. So it's kind of like this, and up here it's going to be like that. Cool. There's our nice cyclohexane. All right. Yeah. All right. What about what number are we on? We're on number 6, cyclohexane. I'm always doing this little structure of my lectures where I give section numbers. They don't always match the textbook, but they're pretty close. Alright, cyclohexane is a strain-free molecule. Alright. Another thing about cyclohexane is that the cyclohexane chair, it's called a chair. It doesn't look like a chair really, but that's what they call it. Chair conformation. What do we mean by conformation? The conformation means the arrangement of the atoms and the angles, and it's called a cyclohexane chair conformation. And there are other conformations of cyclohexane, and we'll mention them. This is the key one to be able to draw and know the most about. The other ones you can draw, but they're going to be a little a little difficult to draw. And anyway, so it can be flipped. From one side to the other. The chair conformation of cyclohexane can be flipped. I'll show it real quickly. I'll draw a little mini chair down there. That's one chair. And it can flip, and it's in equilibrium. So it's not resonance, right? Resonance is the other kind of arrow, and that's just a movement of pi electrons. But it can be flipped to kind of the opposite direction. So, like that. And it's a little, if you're used to drawing this, sometimes this is a little hard to draw. You draw it the same way. Draw the lines the other way, connect two lines, and then connect the other ones. So yeah, this chair can flip to this chair. Okay? Now there's a really important thing about flipping that I'm going to mention. Upon flipping, axial substituents, anything that's axial substituents, will become equatorial substituents. All axial substituents become equatorial substituents after flipping. And you might expect that equatorial substituents, EQ, equatorial, will all become axial substituents. So everything that was axial becomes equatorial, everything that was equatorial becomes axial. Okay? The other thing this is really critical when we draw flipping, is that all upward substituents stay upward, and all downward substituents what do you think? Are they going to stay upward or stay downward? Downward stays downward. Upward stays upward, downward stays downward. Okay? I'm going to draw this, an example real quick. Alright? So, if I have, start with a cyclohexane, and I'm going to put a CH3 right here. And I'm of course, if the CH3 is going up, in equatorial, the H is going down in axial, right? And I'm going to flip it. I'm also ignoring all the other H's because they're not that exciting, and it's defeating what I'm trying to talk about. I really want to talk about, you know, where the methyl, the CH3 is. Okay. Now, when you have to do these on quiz problems, you are going to have to draw the H's in, so practice it. In this example, though, just skip them. Okay. All right. So, what's the flipped chair look like? It looks like this. Right. That's the chair, the flipped chair form. Okay. Make sure you draw that nicely. All right. So there's your two flipped chair forms. What are my rules? Axial goes to equatorial, equatorial goes to axial, right? Now, so this was equatorial. This is up and equatorial, right? And the other rule was upward stays upward, downward stays downward, right? So if this was up and equatorial, here it must be up or down with the rules. Up and equatorial, it's got to be up here, right? That's rule number 2. Upward stays upward. Okay? Alright, so it's got to be upward. And it went from equatorial, if it's equatorial, it changes to axial. It changes its position. But the point here is really important that it goes from up and equatorial to up and axial. And this position here, where it looks like it logically should be, right? It logically seems, oh, you know, it's bottom left here, maybe it's bottom left there. Well, it can't be there, because that right there is it would be if it has to go to axial, well, axial's downward here, right? Axial would be straight down, right? Okay, so it can't be there. It's got to be either there or there, because those have an up and axial position, right? So this is an answer of how it flips, H3C. Okay, where's the H? It was from down and axial, now it has to be down and equatorial. Well, it would be like right there. Okay, so this position in the left chair form, becomes this position in the right form, the flipped form. A name I like to give this is rotation of perspective. So, quote, we have to rotate our perspective. We have to rotate our perspective. When we draw these flipped forms, we rotate our perspective, and all that means is like we're looking at the molecule from a slightly different angle. In order to see the correct flipped form, we have to rotate our perspective. And I don't think the book says that. It's something I say. And in my lectures, I'm going to say, rotate your perspective, rotate your perspective. And that means that we have to envision where the methyl is going to be one carbon from where it logically should be. It should not be on the bottom left. There's the bottom left here, but it will not be on the bottom left here. It'll be either the top left or like in the middle. Because the middle could be up in equatorial also, sorry, up in axial also, right? It could be up in axial right there also. Yeah, okay, so it's called rotation of perspective. And so we just, from whatever perspective it was in the left, it'll be one carbon over in the perspective on the right. We rotate our perspective. Let's do another one. Okay, here's a chair. It's actually not necessarily the best chair because these aren't totally parallel, but that's, you know, we have a little bit of flexibility. Actually, why don't we, you know, to emphasize good habits, let's fix that up. I have no excuse. I've been doing this for 1,000 years. No excuse. Okay, start with my 2 lines. Go upward, upward. There we go. That's better. That's nice and parallel. Everything's parallel, right? Alright, so let's put a chlorine axial right there. Let's flip it. Chlorine and axial, flip it. Where does the chlorine go now? Well, it was up in axial, so over here it should be up and equatorial, right? So let's draw the flipped form. And which carbon is it not going to be on? It was up in axial here. Which carbon will it not be on here? It won't be there, right? It's got to go from up in axial to what? Up in axial to up and equatorial. That does not have an up and equatorial position. So it's either going to be on this carbon or this carbon. Up and equatorial, okay? Let's draw the H in just for fun. Okay, so maybe I'll pick this one. Right? If it was up and axial, it becomes up and equatorial. There we go. The H was down and equatorial. Now it is down and axial. Okay? Cool. So that is a correctly flipped chair form. You cannot correctly draw it if you use like that position there. Okay? What else? What else about this? What else about this? Let's just draw the. There's another form that we could draw, right? If we look at one carbon over, it could either be, you know, in this molecule, it could either be there or there. Let's just draw the other one just for fun. I'll put it down here also. Okay. So the alternate form. If it was up in axial here, up in equatorial would be where, if we draw the alternate chair form. It would be right there, and it would up in axial to up in equatorial, so it would be like this. The hydrogen was down in equatorial, should be down in axial. It would be kind of down here in the back. I made it really long, just to, because I had that line and stuff. The other thing, notice I tried to segment, like, you see that little segment, like in the back? Because it's in the back. I stopped drying a little bit, I went down, took a little break, and then I kept drying down. That's important if it's in the back, if you're going through the bond like that, because it is behind this line. This line is in front of us, right? Okay, so I tried to do that. I didn't do it too well here. Let's try it again. Okay, let's try this one more time. That's a little better. That's what I'm trying to show in the back there. Now it's very clear that the H is in the back and this line is in front. All right. And remember also with chairs, we never use the wedge or the dash bonds to indicate three-dimensionality. We just don't do that. We always use, it's very obvious the way we draw this, what's in front, what's in back. That's in front, that's in back. We don't need to use the dashes and wedges, okay? Okay. Alright, so I'm showing what I was just talking about with my models here, and hopefully you can see it. So I'm showing, this is methyl cyclohexane, right? So there's ch4, and we got the cyclohexane, everything's nice, and we got some axials, we got some equatorials. You should totally do this with your own models, assuming you have your own models. Make something like this, right? Methyl cyclohexane. All right. And so what I want to show is that, you know, the effect of like flipping the chair. And so this carbon right here, with the equatorial methyl group, is going to flip. When it flips, right now it's up in equatorial, right? Where's it going to flip to? Up in equatorial becomes up in axial. So it's going to flip up, and the other side of the ring has to flip down. Okay, so it's kind of a two-step process. This guy flips up, this guy flips down. All right, and so you have to apply a little bit of pressure here. So I'm going to apply some pressure for this all to happen, and I'm going to flip this up. Okay. Interestingly, we're in a weird conformation right now, and I'm going to talk about these conformations in a little bit. They have names too. They're not chairs. We're in no chair land right now. It's like the transition period between the two chairs. Anyway, this guy flipped up, this guy flipped down, and now what was up in equatorial is now up in axial. Previously the hydrogen was down in axial, now the hydrogen's down in equatorial, right? So that shows exactly what I was talking about. Equatorial goes to axial, axial goes to equatorial, up stays up, down stays down, okay? Let's go the other direction, okay? And so let's just for fun switch it around. All right, so now let's say we're starting in the like other side, whatever. It doesn't matter what side you're on. It's all the same, right? If we have something that's up in axial, if I have something that's up in axial and I flip it, it's going to go from up in axial to up in equatorial, right? So I'm going to flip it down. I'm going to apply pressure to flip it down, and then the other side is going to flip up. Okay? So right now we have a ch4 that's up in axial. It's going to go down to up and equatorial. So flip down and flip the other side. It's like a two-step process. Flip one, flip the other. Okay? All right. And the rotation of perspective just kind of happens when we have our models, because you have to look at the chair, which is you know, the frame of carbons, and that does change a little bit when you do this. It's a little hard to see through the camera, so anyway, what I showed on the drawing applies to when you're doing drawings, but it's exactly the same as I'm in my hand. It's just a little hard to represent when I'm doing this with a camcorder. Okay, with your models, though, you can see that, and you know, my guidelines for how to draw cyclohexanes are they work every time, so I would just do those. All right. Now we're at up and equatorial. Let's flip back to up and axial. So two-step process. Flip this side up, flip this side down. Yeah, opposite side, right? Flip this side up, flip this side down. Okay? Alright. Now what we're going to see also in a little bit is if you have two substituents, like if I have another ch3 like on this other side, they both flip the same way. This is a preview to what we're going to see in a few minutes. Alright, so let's just say now we have two ch3s, one that's up in axial, and on the other side it's down in axial. When I flip this guy up and I flip, yeah, if I flip this guy from up and down in axial and I flip this one up in axial, they'll both become equatorial. So this goes to up, down in equatorial, this goes, whoa, uh-oh, what's going on here? There, let's try it again. Okay, we're chair, nice chair. Both are, one's down in axial, the other's up in axial. This guy flips up, this goes down, and now they're both equatorial, but the directions didn't change. Now they're, one's down equatorial, the other's up equatorial. Okay? Alright. Alright, another example, and we're moving slowly to having a couple substituents on the cyclohexane. Let's draw a chair. Nice chair, everything's, the angles are relatively the same. This one's maybe a little messed up. Let's fix that one. Okay, and let's put a CH3 up here, up in axial. Where's the hydrogen? Down in equatorial. And then this position, let's make it fun and make a CH3 up in equatorial, and this H will be down in axial. Okay. What's the name of this molecule? It's 1,2-dimethyl, well, because you have two methyls, right? And the numbering would be the same because both of them are methyl. So it's 1,2-dimethyl cyclohexane. 1,2-dimethyl cyclohexane. Is it cis or trans? Looks kind of, they're in opposite directions, right? When you're looking at cis and trans, you're not caring about what's axial and what's equatorial. You're looking at the relative orientation, right? So this is up, that's up. That's up, that's up, right? They're both up. So is it cis or trans? It's cis. Cis 1,2-dimethyl cyclohexane, right? Let's draw the chair flipped form. Okay, alright, so I'm going to just arbitrarily label this number 1 and this number 2. Okay, so it's and it's kind of a clockwise orientation. It's like 1, 2, 3, 4, 5, 6. Right. There's no. This has nothing to do with the numbering. It matches 1,2-dimethyl cyclohexane. But what I want to do is I want to keep my orientation the same as I go from this molecule to this molecule. So clockwise here, clockwise here. Okay. All right. So what else? The top right carbon is up in axial, right? Over here it has to be up. It can't be up in axial. It has to be up in equatorial, right? So where is that carbon going to be now? It can't be there. It can either be there or there, right? And it's your choice. I can either say 1, 2, or I can say 1, 2, right? But I can't say 1 there. 1 is impossible. Carbon 1 that is here cannot be carbon 1 here because the orientations are going to be wrong. because it goes from up and axial to up and equatorial, and there's no up and equatorial position at this. Here you have an axial up and an equatorial down, right? Okay. What's the other name for that concept? Rotation of perspective. Remember, rotation of perspective. Rotation of perspective is that concept. Okay, so I'm going to just maybe, I don't know, it's really your choice, 1, 2, or 1, 2. I'm going to do this as 1 and this is 2. So it went from up and axial to up and equatorial. And I'm not going to write CH3 because the line also implies CH3, and also because I have a line right there. You could write CH3 there if you want. Okay? I just can't because I don't have any room. And then if that's 1, where's 2? We have to keep our same orientation. So it's clockwise here, clockwise here. So if this is 1, 2 is there. This is your second carbon, and it was up and equatorial. Now it is up and axial. Okay? Here's my 1 and 2. So we kept the same orientation. It's kind of clockwise around the ring, clockwise around the ring. What I'm trying to say though is don't go from like clockwise here to counterclockwise here. Keep you the same orientation. Okay, where's the hydrogen on number 1? It was down in equatorial, now it's down in axial. Where's the hydrogen on number 2? It was down in axial, now it's down in equatorial. And the way we drew it, it's got to be actually off to the right. So I gotta erase my 2 for a second. And what's the parallel to? H is parallel to 1 bond over, so it's parallel to that and that, right? So there's our H, that's parallel to 1 bond over. Okay. To make this a little nicer, it might be useful if you get your eraser out and just erase a little bit of the ring there. And so the CH3 is very clear, and there's a little gap in the ring because it's in the background, right? That's how we kind of suggest that. Anything else? I don't exactly, my bond looks a little bent. It looks a little bent to the left. Let's fix up the bond, make it nice and straight up axial, okay? A little better, okay? We got the little gap in the background, alright? Very cool, and in your paper maybe write CH3 right there, just to be consistent. And let's write 2 here. Okay, so very nice. We're maintaining our clockwise orientation. Specifically, also, we don't call the carbon 1's here, it's not carbon 1 there, carbon 1's there. It's part of our rotation of perspective, okay? Real quickly, I'm gonna show the same kind of situation, but with my models. So this is also cis-1,2 dimethyl cyclohexane. Cis because they're in the same direction. The methyls are in the same direction. That's the definition of cis. What's the definition of trans? Opposite directions. Okay. So cis-1,2 dimethyl cyclohexane, and when I flip, I usually grab one end of the molecule and I grab the other end. So I'm going to flip like this one downward from up in equatorial to up in axial, right? And then I'm going to flip this up. I'm going to flip the other side down. Okay, that's how you do a chair flip. All right, and when I watch what happens, I apply pressure, 2-step process. I'll flip this up, flip the other side down. Now I'm in a new chair. Okay, and when I did that, I rotate my perspective one way or the other. Okay, and with the models, rotation of perspective means I just rotate the models a little bit. That's not totally critical for you to understand, you know. But when we draw it on paper, you always have to rotate either one carbon to the left or one carbon to the right, okay? But we're kind of doing it intrinsically when we flip our models, okay? Because all up stays up, down stays down. Always, 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 no exceptions, okay? Let's go the other way now. I'm going to take this carbon, which is the up and equatorial one, it's going to go to up and axial, flip the other side of the molecule down. Now we have a new chair. We can, you know, there's a lot of ways we can rotate this around, but the big thing is up stays up, down stays down. Try this with your own models, all right? Try building 1,2-dimethyl cyclohexane and see if you can flip it, okay? And notice how up stays up, down stays down. All right. There are also some unstable conformations. What's the one we were just talking about? What conformation have we been focusing on? It's what you're sitting on right now, probably. Chair conformation, right? But there's a couple unstable, like, kind of intermediate conformations. And when I've been flipping my chairs, I notice them, because it's a two-step process, right? I flip one side up, I flip one side down. But there's intermediate conformations in between those. And I'll draw one of them. This is not a major thing for the quiz or exams. Not major testable item. Not a major testable item, so don't worry about that and being able to draw them. What would you be drawing, like on the quizzes and things like that? You'd be drawing the chairs, right? I kind of like to focus on the chairs, but these are other things, and we just need to be aware of them. Okay, so I am going to draw boat cyclohexane. So boat cyclohexane is kind of like the extreme intermediate between the two chairs, like the midway point. Okay, and you can draw kind of like this. Looks like a boat, right? Well, that's the middle point, and the CH2s are kind of poking up. You don't really have axial and equatorial anymore. They're all actually kind of eclipsing, right? A lot of the neighboring CH2s are sort of eclipsing. So these are all eclipsing. What's the type of strain that is associated with eclipsing interactions? It begins with T. It's torsional strain, right? And it's disfavorable, right? Strain is always disfavorable, right? Yeah, so this is like a midway point. It's actually a transition state between the two cyclohexanes. I'm going to show this on the video in a second. There's a couple other like intermediate conformations. Whoops. The others are twist-a-boat and half-chair. Okay, and these are kind of in the intermediate states, and we will. I'll show these with my models in a second, just to understand what they are. You never have to draw these. The book shows them, but you don't have to actually ever draw them. So don't worry about like drawing the twist boats and the half chairs. It's easier to see them with models. So and feel them. There's an interesting case where you can sort of feel them with models when you do the chair flipping process. So that's what I'm going to show you. is, and there's also a little energy barrier as you go through, you know, at one chair to the intermediate forms, and then you go to the other chair. Okay, so this is a rare case where you can actually feel the energy in the different models as you go from one extreme, like one chair form, to the other extreme. Okay, all right. So let's try that. Alright, so this is actually one of the slides for Chapter 4, and I'm going to kind of step through it, and then I'm going to switch to my models. And with this looks kind of scary. Don't be too scared of it. What this is showing is kind of like we start with the low energy conformation there on the left. This is one of the chairs, right? What we're going to see is I'm going to demonstrate this with my models, that it's actually kind of a lot of energy, you know, relatively speaking. When I'm pushing on my my models, right? I want to flip it. I have to apply pressure. You saw that earlier. I was like, oh no, you got to, you know, I can overcome it. I'm a reasonably half-strong human. I can actually use my fingers and overcome the energy barrier, but you can see the energy barrier here, right? There's an energy barrier. It goes all the way up this mountain, and that's why I have to apply a moderate amount of energy to overcome this to make the half chair. The half chair is a transition state between the chair and something called a twist boat. Okay? I actually can't really experience the half chair with my models because it's you know, your models are, if you hold them there, they'd probably break, right? So you kind of, it's a little mountain. You climb over the mountain, and then you're into this twist boat territory, and then there's like two twist boat conformations, and then there's the boat that's in the middle. The middle is a small transition state between the two twist boats, right? So I'm going to go from chair over the half chair, which is hard to visualize. It's a high energy intermediate. Then I'm going to be in twist boat territory, goes back and forth, with the intermediate being a boat, that small transition state. I can actually kind of see this. And then it goes from twist boat all the way over another half chair into the other chair form. Okay? These slides are in your notes, and if you have models, this is a great exercise, not only in just, you know, visualizing the molecules, but also visualizing the energetics of this pretty complicated energy diagram, right? It's pretty cool. All right, so let's check it out with my models now. All right, so let's see here. Now I'm just showing cyclohexane. I got rid of the substituents because it's not needed for this exercise. So I got my chair cyclohexane. And yeah, like I said, you know, if I'm flipping it, there's actually, I have to apply a little bit of energy, right? I have to, like this side is up in equatorial, down in axial. I got to flip it up an axial. I have to apply pressure. It doesn't just do it. If you have really flimsy, rubbery models, yeah, it's hard to do it. But actually, some of the challenge with some of the models is they're not rigid enough. And so you can't really see this, what I'm trying to do. These models are actually kind of cool, but they're hard to get. You can't find these on eBay or anywhere anymore. And they are nice and rigid, so they demonstrate this nicely. Okay, so I am going to flip it, and there's a transition state, which is the high energy intermediate. I can't really hold it there. I can shoot over the mountain. You have to be looking at that little figure I was just showing. It's also on the website, so maybe go get that figure out, or you know, you just saw it. But yeah, there's an energy barrier transition state. I'm going over the mountain, Okay, I went over the mountain. The half chair is kind of the midway point, right? It's the high energy thing that I can feel with my models. Now I'm into the little valley where we have twist boats, and then these two kind of half chair things that are actually pretty, you know, just flexible. But and then there's the little mini mountain right in the middle, and that's a little high energy because things are, you know, the most eclipsing, most torsional strain. Let's look, and you can see the torsional strain right there, and the eclipsing interactions, because everything's eclipsed, right? And then I flip to the other side. So, whoops. And you can see and feel that I jumped over the other side of the mountain. Okay, let's do it again. So now I'm going to flip the right side. So I'm going to flip it over the high energy transition state. I feel it. I flip it over. Now I'm into the low valley. Flexibility. We have the little valley, and I flip the other side over the energy barrier, and now I'm here. Okay, so that's it. That's pretty cool. It's a case where you can actually visualize the energetics of chair flipping with your models. All right, moving onward. We kind of introduced cyclohexane and the different how to flip cyclohexane, some of the different alternate conformations like half chairs and twist boats. But the chair one is the most interesting for the general structure of cyclohexane. Let's talk about substituted cyclohexane. Probably for the testable, quizzable topics, this is a big deal because you're going to do some cool calculations. They're not difficult, but we will be doing them to kind of figure out the which substituted cyclohexane chair forms are the most stable. Okay, so in order to do that, we first have to recognize that equatorial substituted is more stable than axial. Equatorial substituted cyclohexanes are more stable than axial. It's pretty easy to see that. So let's just draw cyclohexane, CH3. Here we have an H up, CH up in axial, CH3 is down in equatorial. Not the best flipped form, but yeah, that suffices. Alright, this was down in equatorial, so that must be down in axial over here. Which carbon can you not draw it on? You cannot draw it on that one, right? Can't draw it on the top left, so maybe we'll put it on the top right. Can't put it on the top right, maybe we'll put it on the bottom right. So it was down in equatorial, now it's down in axial. H was up in axial, now H is up in equatorial. Very cool. Alright, there's our molecule. Who's more stable? I already said equatorial substituents are more stable. So the CH3 being the kind of large substituent, because H is also a substituent. The H doesn't really matter though in terms of where it is. CH3 does matter. And why does it matter? Well, first of all, let's write more stable, less stable. Why is the right side less stable? It's an interaction between the CH3, which is down in axial, and this H and this H in the distance. The CH3 kind of gets in the way of those two things, those other axial substituents. And this is given a name because of where the CH3 is. It's like 1, 2, 3, 1, 2, 3. The name, as you might guess, is called a 1,3 diaxial interaction. And it's disfavorable. Okay? 1,3 diaxial interaction, and it's disfavorable. 1,3 diaxial interaction. That's disfavorable. Okay? generally speaking, he's the more stable. Equatorial. Versus axial, equatorial is always the stable one. What we're going to see though is if you have a couple different substituents, then there's going to be a competition, and we'll show you how to resolve that competition. There's another way to see this. I love this way. This is very easy, right? 1,3 diaxial interaction is very easy to see. In reality, it's also similar to a Gauche butane interaction. Gauche butane, remember Gauche butane or Gauche interaction? What was that? Where did we see that before? The Gauche butane. Well, Gauche butane was back when we talked about butane, right? And the rotational isomers of butane, and we saw this with a Newman projection. Remember, like if we drew butane, we had a few different conformations of butane, but one of them, well, I'll draw it on this side, was staggered. It's not eclipsed, right? That's not eclipsed. Is it? No, it's not. It's staggered, right? Eclipsed would be if you had, you know, everything lined up. But this is a staggered conformation of butane, and it's gauche, right? Because those two things are bumping into each other. What was the good, happy conformation of butane? It was called anti-butane. So this is gauche. Anti-butane had the CH3s away from each other. That was the happiest conformation of butane. But anyway, this is a little bit of an energy barrier. There's a figure in the book that shows how axial substituted cyclohexane is also kind of like a Gauche butane interaction. I just like drawing it this way, but let's just show it. We'll show the figure. It's figure 412. And I have it in my little PowerPoint stack, so you should integrate the PowerPoint into your notes. I know if you don't have a printer, it's hard, but you should you know, at least have it online that you can look at all of those slides for each of the chapters. And maybe, you know, in your notes you can write see PowerPoint stack figure 412. All right, so let's take a look at that now. Alright, so this is from that PowerPoint for Chapter 4. What we're seeing first, and I'm covering up the right side of the slide, is what we have with equatorial substituted cyclohexane, right? And we're going to draw a Newman projection, kind of, that's a little eyeball, I don't know if you can see it. The eyeball is looking at that carbon, and we're like looking at that carbon and draw a Newman projection. Remember with a Newman, it's like a dot and a circle. The dot is the close carbon, and the circle is the far carbon, right? So it's like, here's the middle of the Newman projection, and this is the far distal one. All right, so let's take a look at what the Newman projection looks like. As we're looking down that initial carbon, and you can kind of see where's the Y group. The Y group, the substituted carbon, is kind of off out to the right, and it is anti to the CH2 group. What's the CH2 group? It's this one, all right? Right? It's up top there, right? That's coming downward in the distance, right? That's that CH2, because the circle again is the far carbon, the dot is the close carbon. Okay. Anyway, it looks anti. That's actually kind of, you know, when you think of butane, that is actually the happy butane, right? The happy conformation of butane. So now let's look at what happens if it's flipped. And notice, here's an interesting thing. Notice how the eyeball is looking at a different location, right? Because the Y group was up in equatorial, now it's up in axial. Why did they do it this way? Why did they put the Y group on a different carbon? Why didn't they just put the Y group down here on the bottom? Well, remember, it has to go from up in equatorial to up and axial, and there's no up and axial position there. So what did they do? They rotated their perspective, just like I told you you should do, right? And anyway, so Y goes from up and equatorial to up and axial. Now we're looking down this bond, and what do we see? And also, like I said, axial is the kind of disfavorable one because of the 1,3 diaxial interaction, right? Okay, so let's zoom in there a bit. Now you can see that the Y group is actually kind of interacting with that CH2. You also see the 1,3 diaxial interaction. But what did we just say is another way to visualize this? The Y group is experiencing a Gauche butane interaction with the CH2. It's just like the Gauche butane we saw in chapter 2. And so that's a Gauche interaction, right? So that's another way to show that axial is relatively unhappy compared to equatorial, which is relatively happy. Okay, so this I think is figure 412 from your book. You can also take a look in the book. All right, so yeah, what's the takeaway? Equatorial good, axial bad. Okay, you're not going to have to draw this or show this type of thing in the quiz, testable content in this course. But it's just another way to understand axial's bad, equatorial's good. Okay. Okay. So we just learned that equatorial is a little more stable than axial, right? Let's see if we can quantify this. Extent of 1,3 diaxial interactions. (1,3) diaxial interactions. What's the extent of these 1,3 diaxial interactions? And that kind of just tells you, how unstable is axial compared to equatorial. So let's think about just a simple chair. We have our group there, and it flips unhappily to the axial. Now the R group's down there, for example. Okay, let's look at some R groups. Now what I'm gonna write here is delta G under standard conditions. So it's a energy value. The energy to go from equatorial to axial. Okay, so these are going to be kind of small numbers, but real numbers. As you go from equatorial to axial, is that going to be a positive number or a negative number? Because we're going from something happy to something less happy, right? So it should be a positive number. Okay, of course it'll be a positive number because you're going from something happy to unhappy, right? Equatorial, axial. Alright, cool. So, what are the numbers? First is H. Of course, you should be able to predict that number because if R is H, well then there's no difference because H, you already have two H's there. CH2 to CH2, there's no difference, so this is 0. These are all kilocalories per mole. Cool. What about, and I'm going to draw a squiggly line CH3. So the squiggly line means, that's where it's attached. So it's a cyclohexane connected to CH3. The squiggly line means the attachment point. Okay, and it is 1.7. So that's a real number, right? And that's showing that when you have methyl cyclohexane, the energy difference, the free energy is 1.7 kilocalories per mole less happy when it's axial due to the 1,3 diaxial interactions. The 1,3 diaxial interactions. Okay. Now, what do you think a slightly larger thing, like ethyl, would be bigger number or smaller number? Should be a small number or a big number? Well, it might be a little larger because the interaction is going to be greater if you have a larger substituent. So maybe it's a little larger, and it is. It's not a ton larger, but it is it's noticeably larger, 1.75. All right. What about, what's that group called? Squiggly line, 3 carbons. 3 carbons, squiggly line on the middle. We learned the name. It begins with I. And it's 3 carbons. So it's something propyl, right? It begins with I and it's something propyl. So it's isopropyl. That's an isopropyl group. And bigger number or smaller number? Well, it looks like there's 2 CH3s off a central carbon. You might think it's a little larger, and it is. It's 2.2. Alright? Slightly larger. What about squiggly line and 4 carbons? 3 of them attached to a central carbon. What's this called? It's a butyl, because there's 4 carbons. It's one of the butyls. What is it? It's something butyl. Tert butyl. There's isopropyl, tert butyl, T-E-R-T, butyl. 5. This is a huge number. Relatively speaking, it's one of the biggest numbers, actually. If you do like 1,000 different things, this is one of the larger ones that can exist in a cyclohexane. Okay? Also, I should say that these are the interaction, the 1,3 diaxial interaction is called a steric interaction. A steric interaction, which we talked about before, also with rotation of butanes and stuff. Like Gauche, the reason Gauche is unhappy is because of a steric interaction, right? What is a steric interaction? A steric interaction is a through space interaction between a couple of things. And if there's a diaxial interaction, let's draw the diaxial. This is equatorial, this is axial, right? HH. There's the interaction, right? It's a through space interaction of the R group to the H's and the carbon atoms, and as the R group gets bigger, the interaction gets bigger, right? And that's what we see. Tert butyl is a huge thing. It's huge. You have 3 CH3s off a central carbon. It's a huge number. Okay. All right. So now let's try a couple other ones. Fluorine. Big number, small number. Well, what's the size of fluorine? Is it a big thing or a tiny thing? It's actually really tiny. It's almost the size of a hydrogen, right? It's almost the size of a hydrogen. And so if you compare a fluorine to like a CH3, is this going to be a big number or a small number? And it's a tiny number. It's 0.25. Because it's way smaller than a CH3, right? And then a chlorine is also smaller than a CH3. It's 0.52. Bromine. Bromine, is that larger or smaller than a chlorine? It's a little larger, right? And is the number going to be smaller or larger? It's going to be slightly larger. Iodine. Iodine. Bigger or smaller? It's bigger. So the number should be bigger as well. But it's not. It's an anomalous one. It's 0.46. So we'll put a exclamation question mark. Why is it smaller? I think what the book says and what I've kind of gathered in my own research, the reason iodine is a smaller number, even though the atom's bigger, is the bond is longer. Bond is longer than like the other halogens. And with a long bond, if you imagine if the bond is really long, that's going to decrease the extent of the interaction. So iodine is a little bit anomalous here. Okay. There's more in table 4.3. So if you need more, there are more. You can check it out. We're going to use these though in our calculations. So these would always be provided to you in your quizzes and things like that. All right. All right. So let's see. So we can predict the dominant conformation. And this is a strategy I created myself, so it's a little different than the way the book does it. But I really like my way, and since I created it, I'm going to take credit for it, and I am going to make it a magic word. And the magic word is going to be pizza. I love pizza. Another food item. So the magic word for predicting the dominant conformation is going to be pizza. Alright, so we got some pizza here. Let's try out an example, and I'll show you my method for predicting the dominant conformation. Alright, so if we have methyl-methyl, 1,1-dimethyl cyclohexane, 1,1-dimethyl cyclohexane. And let's draw the alternate flipped form. Okay, so rotating our perspective, the methyls were up and down, and on that carbon, but now they're going to be maybe on this carbon or that carbon, because we have to rotate our perspective. Never forget to do that. So yeah, CH3, CH3. Well, this is an easy one. We don't have to do any calculation. Of course, is there any difference between these two energetically, do you think? Well, they both have a methyl that's axial, and delta G is 0. Meaning there's no difference. The equilibrium is 50-50 here, right? But let's try bromo equatorial. And what is the flipped form? Let's make this nice. My chair is pretty bad. Let's make the chair nicer. Okay, so there's chair bromo cyclohexane. And what I'm going to do to demonstrate my technique here is draw the flip form. Where's the bromine going to be now? Not on this carbon, but maybe this one or this one. So I'm going to arbitrarily make it go from up in equatorial to up in axial right there. The H is going down. Alright, there we go. So to demonstrate my technique, this is how we do it. Okay. Delta G is going to be the sum of delta G equatorial to axial. Sounds scary, but just bear with me. And left side minus the sum of delta G equatorial axial on the right side. Okay, so let's do this. First of all, in this example, we have a bunch of H's, right? What's the delta G value for H's? 0, right? So there's a bunch of H's that are all 0, including the H's right there, right? So the way we do this is a very simple process. All we're doing is we're looking for things that are equatorial. Okay, that aren't H, right? And on the left side, what is equatorial that's not H? Everything's H, except for that equatorial Br. What's the number for Br? Look in the table, 0.55. Okay? Now, that's the whole left term. Is everything on the left that's equatorial. Everything that's on the left, equatorial, you have to get the number, right? From that table, which is essentially the energy from going from equatorial to axial. And we're looking for only equatorial things, okay? Now we look on the right side. What is equatorial? A whole bunch of, you have H's that are equatorial, but no, the Br is not equatorial. All the H's are 0, so we sum it all up and we get 0. This is the mark method. It's really easy, and it gives us a quick answer. So the answer is 0.5 kilocalories per mole. 0.5 kilocalories per mole. Okay, so is that it's a positive number, right? So who is the favored molecule? Well, we know that, between the two, obviously the left is going to be favored because it's equatorial, right? But we also, now we know the delta G value. It's 0.55, which is a left favored equilibrium, right? When is it a right favored equilibrium? When delta G is negative, as you've learned, right? Okay. Alright, so let's try another one. Let's try another one. When you do a couple of these, it'll be really easy. The main thing is all you're doing is you're adding, you look at the left and the right, you look for things that are equatorial on the left, add them up, look for things that are equatorial on the right, add them up, and you take the difference. That's how we got 0.55 on the left, okay? Let's try another one. So I'm going to draw cyclohexane with a methyl going up, alright? And then let's draw the axial, up and axial, right? So we're asking the question of which direction is this equilibrium going to go. Just like above, we ask the question of which direction is the equilibrium going to go. Alright, so draw the alternate chair flipped form, and it went from up and axial to up and equatorial. Delta G equals the same thing, equatorial to axial on the left, minus the sum delta G equatorial axial on the right. Okay, so how do we do it? We look for everything that's equatorial on the left, and there's nothing except H's, so it's 0. That's the whole left term. On the right, we look for everything that's equatorial, aside from H's, because H's are 0 anyway. We see a CH3, it's equatorial, right? And we get the number, it's 1.7. 0 minus 1.7 is, get your calculator out, negative 1.7. Okay. And of course a negative delta G is product favored, or right side favored. And so yeah, this is totally favored. So we get delta G of a negative delta G, it's right side favored, and of course equatorial is more stable, so yes, it's totally going to be favored on the right. That's so easy. The book does not present it this way. I don't like the way the book does it. We'll try a couple more. Alright, it's another one. Let's make a CH3 up there and a BR there, HH. Now it's going to get more complicated because we have two substituents on there, right? Okay, and so we got two substituents on there, and How do we do? How do we draw it first? The alternate form. So Br is on the bottom there, down, up in equatorial. So it must be now up in axial. We're going to do that thing I recommended before, where we pick an orientation, 2, 3, 4, 5, 6, clockwise, for example. And we want to maintain that clockwise orientation when I draw the alternate form. And where is the Br going to go? It can't go there. If it goes here, it cannot be there. It's got to be there or there. So I'm going to put it up there. Up in equatorial to up in axial. Okay, so now it's going to be 1, 2, 3, 4, 5, 6. Okay. So we rotate our perspective. And it goes 1, 2, 3, 4, 5, 1, 2, 3, 4. So now the CH3 was up in axial and it's up in equatorial. Draw our H's in. Very nice. Alright. Okay, so let's do the delta G calculation. Whoops. Delta G is essentially left minus right. We sum up the things on the left, we sum up the things on the right. They're always the equatorial delta G values. I'm not writing in all the text here, but that's fine. Alright, so what's equatorial on the left? Br. Only Br, right? Oh yeah, but before we even do that, what do you which one do you think is the favored one? You should be able to make a guess. Which one do you think is going to be favored? The favored one is going to be the one with the big things equatorial and maybe the small things axial, right? So which is bigger, a Br or a CH3? We did the numbers and we saw CH3 has a larger delta G. So methyl would rather be equatorial, and it takes precedence. It's going to really want to be equatorial. So this is probably going to be the favored one. We did this just based on our understanding of the size of these things. So we're going to predict it's going to be the right side. So we're going to predict that the delta G will be positive or negative. Well, delta G is probably going to be negative if it's the right side. So we have a prediction. Let's see if we can do the calculation real quickly. Left side, we sum up everything on the left, that's equatorial, and it's 0.55, right? Right side, what's equatorial on the right? Not the Br, but the CH3. 1.7. Do the math, and it's negative 1.15 kilocalories per mole. Isn't that cool? So we determine delta G, it's negative. So we actually have a calculated delta G, a predicted delta G, that's showing that this is going to be the dominant conformation, the right side, with the larger thing being equatorial and the smaller thing being forced to be axial, right? Anyway, we have a couple more examples of this. I'll announce what's going to be on the quiz on the iLearn site. And very likely we are not going to do this calculation until the next quiz, but we're going to have a couple other quiz things on cyclohexanes on this upcoming quiz, cycloalkanes, you know. So yeah, look in iLearn and I'll tell you what you might expect in the quiz. But these kind of problems, it's really easy. It's really easy. It's not going to be on this quiz. I think I'm just going to push it to the next quiz. All right.